All right, so we'd like to continue session 4 on the formation of primordial galaxies and observations at high Z. Our invited review speaker to kick off the afternoon session is Gnedin, who is speaking on cosmic reionization and background radiation.
So I was supposed to speak on reionization and background radiation, so I actually know nothing about background radiation, so I'll pretend that I ran out of time. What I'm going to do is, I'm sure you heard a lot of talks about reionization, and you know all of this stuff, so I'm not going to really review all the details. I would like to see more like for the future where we're actually heading and what we hope to learn. And I put this provocative second title, 10 more years and we are done. So I will start with an epigraph. Normally you don't put epigraphs on scientific talks, but I really like this phrase from Peng O, who claimed that reionization is interesting because it's the last time the whole universe did something together. After that, baryons did something on their own. And so, if you think what we know about reionization today, it's already a very impressive set of observations that we have. So the galaxy luminosity functions, right, one of the most important property of describes sources of reionization, are measured all the way to redshift 10, thanks to HST and different deep fields. And in fact, thanks to frontier fields and using gravitational lensing, these luminosity functions are actually extended at the lowest end in some studies claiming going all the way to -12 or -13. Which is roughly the JWST reach without the lensing. Actually, it's beyond JWST reach without lensing. So, the sky redshift galaxies are not only observed as points of light, they have spectra. They're also observed in the infrared with ALMA, at least some of them. And so we have things like infrared access and UV slopes that probe the amount of dust that exists in those galaxies. And we also know that UV slopes behave in a non-trivial way, and some of those galaxies are really extremely blue. Only a few years ago, there were claims that they are bluer than dust-free, so there were claims of negative dust abundance in them. But they're really extremely blue, so they have very little dust, but at the same time, they do have dust, right? So it's little dust, but it's there. We also know that they're highly clustered. The clustering of galaxies has been measured all the way to redshift 8. For reasonable samples of reasonably bright or faint galaxies. We also know that Lyman alpha emitters, which are now observed all the way, actually not observed to redshift 8, but could have been observed to redshift 8. We know the fraction of galaxies, of Lyman bright galaxies, which are Lyman alpha emitters, are rising with redshift to redshift 6 and then start dropping down. And again, this has commonly been interpreted as a signature of reionization, that the universe becoming neutral absorbs Lyman alpha and sort of hides Lyman alpha emitters from our view. Finally, the high redshift quasars, the number of them was increasing very rapidly thanks to recent surveys. This is already a highly outdated plot. There are 60 plus quasars above redshift 5.7. I think the last time I checked, the count was exceeding 100. And number of quasars between redshifts 6.5 and 7 is also increasing very rapidly. There are 3 here, but I think there are 6 or even 9 maybe today. And having so many high redshift quasars allows you to probe the IGM in front of them to much greater details of what was possible only a few years ago. So the most recent measurements will give you the distribution. So there are so many quasars that you can actually look in the redshift bins and measure the distribution of optical depths, not like an average or RMS, but actually the whole PDF of the distribution of optical depths in different redshift bins in the IGM right after reionization. Those measurements are actually highly constraining because simple models don't fit them, as you can see. So they tell us something very important about what happened at the very aftermath of reionization. And finally, the tau, the story of tau is everyone knows, and I'll repeat it a little bit later. You can probably make a blockbuster movie about the story of tau. But the latest value from Planck is 0.58%. So it's going down, down, and we're all waiting excitingly when it gets below 4, then it becomes really interesting. But hopefully it will stay at this value, because going anything lower than that will prevents problems. But all we know today is really light drizzle before a thunderstorm. Right? So the things are going to become really, really exciting really soon. Right? And that's because of this all observational efforts that are going to happen in the next 10 years or so, actually even less than that. ALMA is already observing those high redshift galaxies and measuring dust abundance in them. Hyper-supreme cam on Subaru is going to make a very important contribution, as I'll show you next slide. Because we're all waiting JWST. The launch is still in October 2018, as of a month ago, so hopefully it won't slip. Then we all hope that 21 centimeter experiments will finally make a measurement. The Hera is supposed to be operational by 2020. Next generation optical telescopes, GMT, TMT, EOT, are going to be observing beginning of hopefully 2021. So they will increase the samples of high redshift quasars enormously. And then WFIRST will provide another very important view on reionization whenever it flies. So the sources of reionization usually consider two types, right? Stars and quasars. And for a long time, we kind of knew that quasars cannot make it. But this idea that sort of hidden quasars or faint quasars present a significant contribution to ionizing sources, this idea sort of coming back like a phoenix every other 5 years or so. And in the last rebirth, there were some claims from Chandra Deep Field South that there are way more faint quasars than actually observed from, extrapolated from known luminosity functions. And then if you just count the ionizing photons those quasars produce, they make a non-trivial contribution. So hyper-supreme cam on Subaru is going to finally close this question once and for all. Right? It's time scale of probably a couple of years. But the sensitivity is such that there's clearly it's easy to distinguish between normal sort of standard luminosity function of quasars, it's a lower line, and what you expect from the Jalonga 2015 results, upper line. So Subaru will clearly solve this question once and for all. So in 2 years from now, we will know whether quasars contribute anything to reionization or not. So that's the first development that we see. Then, of course, we all know that JWST, it's one of the primary goals, primary science goals is to study reionization. So increasing the depths would be relatively modest, but it will reach this magic -13 magnitude, which is so important for theorists. And it will also be a large precision gain in measuring the luminosity function. So we start seeing deviations from the simple Schechter function fits that everyone uses. Start seeing details on how this cutoff occurs, if it occurs at -13, etc. And plus, we have multiple bands, so we have constraints on dust, on star formation histories, etc., etc. So we have a significant amount of data on galaxies as sources of reionization from JWST. We all hope that sooner or later, 21 centimeter experiments will measure something. And so the paper in MWA, the first 2 experiments are actually done now. The best constraints we have are from paper so far. So LOFAR is now collecting data. We'll see what it's going to bring. And from American point of view, we have American bias, right? We go after Hera. Here is a second generation experiment, hydrogen epoch reionization array. It has startup funding. It has antennas on the ground. It just got the second bunch of funding. And so the hope is that over time scale of a few years, they actually have the whole thing on the ground. And if they don't see anything, then again, we have to go back and start from scratch. Because if the reionization happens as we think it does, then they should see the signal. Finally, these big telescopes, including WFIRST, will be very useful for both increasing large samples of quasars and so modeling this intergalactic medium in the aftermath of reionization redshifts 5.5 and 6, much better. Doing great more detail to already highly detailed studies. And WFIRST will be very important in providing shallow but large area surveys that will allow cross correlations with Lyman alpha emitters. Is 21 centimeter, and everyone who studies large-scale structure now knows that cross-correlation is a buzzword for the next decade. It will be about cross-correlating different things. So the theorist, we can ask a question, how much are we going to learn from all this data? And the answer is actually not much, unless, who knows what comes? Right. We have the theory, right? Because normally progress happens in fields, and the theory and observations are on sort of equal footing. The theory-dominated fields or observation-dominated fields tend to stagnate. And so what we need to do, right, is to develop a better theory to make sure we have theoretical tools to interpret all this data, right? And we can do it. So it's clear today that for anyone who does theory and reionization, that none of the existing models would actually survive, right? The quality of the data will increase so much that we'll all be blown out of the water. And so our task today, the theorist, is not to make new models, right? They will be useless in the future, but actually to develop new modeling technology, to figure out how we can actually do modeling better, right? And make models which are more precise. And it's actually happening, right? It's not just it's a whole field who is involved in this effort, and there are a large number of serious projects that are mostly based on simulations, but also based on semi-analytical modeling. They are now trying to push this frontier of modeling reionization to much higher level. So Mike Norman already talked about renaissance simulations. Luca was talking about crash. So I will talk about one of those projects, and just to give you a flavor of what we can do, or what we will be able to do when the data come. Right? And so I'll talk about the project I'm involved, because I can plot, I can show you, but I want to put a disclaimer that most of those modern projects are more or less on the same level, right? So we all do comparably good thing, comparably good job, and so this part of the talk could have been given by Mike, could have been given by Luca, equally well, right? So I will give you my bias, but if you think about this as a representative sample, not as an effort on self-promotion, that would be a better view of what we can do. So if you think about how to model reionization, right? Physics reionization is very simple. All we need to do is to have sources, right? Ionizing photons go in straight lines until they hit neutral atoms, and some of those ionizing photons are going to be absorbed by other things. We call them lamina systems, and they will be wasted from point of view of ionizing fresh hydrogen in the universe. Right? So it's basically the story about these two different photons that we need to do well. Okay? So the challenge, however, from a theory point of view is the range of scales. So if we now think about range of scales, we have to model it's pretty large. On large scales, we have to go way more than tens of megaparsecs, because that's where actually sources are. Right? The galaxies are highly clustered. On average, there is one L-star galaxy in 10 by 10 by 10 megaparsec box, but because they're clustered and we want a representative sample of galaxies, we have to go way above 50 megaparsecs moving. On small scale end, we have to go way below 1 kiloparsec, because that's roughly what we need to resolve line limit systems. But you also need to model star formation and emission of photons. For that, you need, depending on how you do it, you can go to hundreds of parsecs or even deeper. But I'm going to argue that we are not ready to go below that scale. And then in terms of mass scales, we have to go to about millions of masses, maybe even lower, depending on what you assume for your model. So in terms of numerical issues or computational issues, we're talking about simulations that range, or models, right? So they're not necessarily all simulation-based, right? So some of them are used semi-numerical, semi-analytical techniques, which are equally viable approach. But we're talking about dynamical range of more than 100,000, and a mass range including 10 billion. But what I'm going to argue is that today, those are not out of the question numbers, right? So those are normal numbers today. We also have to worry about physics. Right? So, but the physics is on a relatively good good account. We know how to model dark matter, gas dynamics, atomic processes, radiative transfer. We can all do it from the first principles sufficiently accurately. The only thing we cannot do from the first principles is star formation and stellar feedback. Okay? And it's also both range of scales and lack of physical understanding. So we have to use it as a subgrid model. But as I'm going to show you, that's also not a problem, because we do have subgrid models that actually work. But before I talk about physics, we talk about numerics, right? I like this plot. This is a Moore's law, which I hope you all have seen, right? That the power of the supercomputer is growing as a function of time. And this is the fastest supercomputer on the Earth. This plot is a little bit outdated. It ends in 2010. But in summer 2013, we were exactly on this point. Now that was the largest supercomputer at summer 2013. It's still there. So as time goes on, of course, those computers don't grow in time. We move horizontally. So today, we moved away from this line. But it did happen in the past, right? We moved up and down. But these new machines that DOE already announced in 2017 will take us back. So far, right, there is any evidence that this trend is stopping. Right? So the computing power grows exponentially. What's actually surprising and funny that powers of notebooks grows with the same rate, just delayed in time. So this is a 500 fastest supercomputer. It's about 6 to 8 years behind the first one, and notebooks are about 8 to 10 years behind. So notebooks actually fall behind the fastest supercomputer on the Earth about 15 years. So the easiest way for you to own the fastest supercomputer on the planet is to take your notebook and go back 15 years in time. But again, that's just a side comment. But what's important for us, right, that the computer's increasing in power. And what's also important for modeling reionization is actually these numbers. So these numbers, 10, 100, and 1 exascale, right, those are really good numbers for modeling reionization, because that's exactly the numbers that allows you to reach this dynamic range in mass and resolution and space. There's also a big progress in doing physics. Right? So as I said, we have to make our subgrid models better. But that's already happening in galaxy formation community. If you read most papers on star formation, on modern galaxy formation, say in 2010, in the first decade of this century, and basically all star formation models said we have gas and it goes into stars. Right? So stars form from gas, and of course observers don't know that's not true. Right? Stars do not form from gas. Right? Stars form from molecular gas. Right? And so today we actually do it much better, right? Because we now form stars from molecular gas. We know how to model atomic to molecular transition. There are many different models. They're all comparable with each other, so you can use whatever one you want. And you also know observationally that there is a very good correlation between molecular gas and star formation on sufficiently large scales. And so that's what we can use to improve our modeling of galaxy formation, star formation significantly. We're actually doing it now. And this is just an example that what I said was true. It is a correlation between surface density of molecular gas, surface density of star formation, Koenig-Schmidt relation. Please don't quote law in front of particle physicists, because they will kill you for that. But this is a relation. Right? We know correlation is very good. It exists at low redshift, it exists at high redshift, and with the same slope. So it's more or less the same relation. There may be differences, slightly difference in amplitudes, which will have to be sorted out. But basically, I would say in the first approximation, we know how stars form from molecular gas on hundreds of parsec scale. Another big thing which happened in the last 5 years, if you actually have not followed galaxy formation community, that the number of simulation projects that now make realistic galaxies increased from 0 to more than 5. I counted 5, or maybe more, right, in just 5 years. So it's a ratio, it's an infinite amount of progress. So 5 years ago, no one could make a realistic galaxy in a cosmological simulation, and now almost everyone makes them. Right? And projects like Illustris and Eagle, the ones which are most famous today, it all began with Eris, one of the first ones that made realistic galaxies, and now make galaxies which look like real ones. So on this large scale, on scales of hundreds of parsecs, you basically understand how to model the feedback. We don't understand how it works, but you know how to model it. Right? And there are even extreme opinions that I heard that basically on few hundred parsec scale, galaxy formation is solved. I don't think it's true, but it's probably not solved halfway. But now we can make large simulations with large number of galaxies. They all look right in general properties like luminosity, sizes, etc., densities, blah, blah. And so using that, right, we can now try to model reionization, right, fully self-consistently. Means that putting everything together and running it all at the same time. So again, I show you what we are doing, but as I said, this is representative of the community. So other people are doing similar effort. They may be doing something slightly different. And whenever we differ, that's genuine differences. We don't agree on everything. But the level of computational complexity that we all have is comparable, I think, at this point. And so we're going to roughly 100 megaparsec box, right, and doing it with many thousands cube resolution elements. going down to hundreds of parsecs and resolving way things below 10 to the 6 solar masses. And this is the range of grid sizes. This actually would something I would really like to have. It's a little bit too expensive for modern day computers, so we have to wait for a few more years for computers to become more powerful. So we can just go relax for a few years, go to the beach and sit there for 3 years, come back, and then I can do that. And what you get when you push this computational complexity to what you can do today is actually a lot, right? So start getting models that agree with essentially all observational measurements. So you get now luminosity functions that I showed you. Again, data points are data points, measurements, and the bands are the simulations, and you start reproducing this evolution of the luminosity functions at all magnitudes and at all times, which means that dark matter halos have right star formation histories for all masses, right? So the whole manifold of mass versus time is covered correctly in this. You start getting galaxies which have right UV slopes, so they have light star formation histories and right spectra. Did I miss something? No. You get this distribution of intergalactic mediums. The one I said is very hard to get with simple models, but in those fully self-consistent simulations, they just come out of the box. Right? You start reproducing this whole distribution of PDFs in the IGM, so it's not like the average opacity, but you actually get a whole PDF, the distribution of opacity in the Lymanov forest at different redshifts and at different values of the opacity. So you get the whole forest right. And you get things like this, a distribution of gaps, for example, right? So the empty regions in the forest, you get them right. So you get a large set of properties of the post-reionization RGM correctly. You get the right amount of dust. Again, this is the same plot I showed you. It's UV slope versus infrared excess. It's infrared luminosity versus UV luminosity. And again, you get things which are similar to what AUM observes. You predict that Lyman alpha emitters should disappear very rapidly between redshifts around 6.7 and 6, which again is what is observed. And finally, the story of tau, I think it's actually a great story, right? Because the simulations, in fact, never change the value. So it's one of those few examples where not the theory matched the data, but when the data actually matched the theory. And the first measurement was, way high, and it spoiled my life for several years. I got papers rejected because of that. Then WMAP9 went down, right? Planck keeps us pushing it down. And you see I have 2 lines here specifically. Those are different runs, and they match exactly one of those Planck. Whichever one turns out to be true, I have the simulation which matches them perfectly. But of course, in reality, what you should take from this is that we can predict tau, but we cannot predict it to 1% precision of it. So we can predict it to within maybe 10% precision of its value, right? So not 10% of tau, but 10% of its value. But doing anything better than that would require much better physics, right? And much better simulations, which we don't have yet. And it's primarily because tau is really a bad number. It's all dominated by what happens at very high redshifts, and that we have to model all those details right to do the exact value. But within the observation uncertainties, we're actually there. Right? And Norbert, could you press this triangle? Right. And there are some things that actually look really cool in the simulations. I'm going to show you what maybe we'll be learning in the future. So this is plot I showed you already. This is UV slopes, the magnitude from the simulations and the data. Red points are, of course, measurements, and the gray bands are the simulations. And when I look at this, I start seeing things. Maybe it's with age, you start seeing things and you get crazy. But there are things which I think I start seeing there. And first of all, it seems like the slope in the data is a little bit steeper than what we predict. And there seem to be slightly more scatter, right? So those are true observational errors. There are actually galaxies which have no dust whatsoever. The blue line is dust-free, UV slope. There are galaxies with -20 magnitude in the real universe, which have no dust whatsoever, not a single dust particle. Whereas, say, in the simulations, we predict some amount of dust in all of them, because we just assume that dust follows metals. And so maybe we start seeing effects of dust being produced dynamically in those galaxies. And so that then JWST comes, of course, all those error bars will shrink. And so one of the things that JWST might teach us is actually physics of dust. Right? Not only history about reionization, but actually how dust forms. And I'm actually running early. No, that's fine. I want to show you a few things that we already learned, right, so far. So as I showed you before, we're actually doing this fully self-consistently and going through the pain of running these very big simulations and dealing with these big machines, which are very, very picky and nervous. So it actually pays because we can start reproducing a large amount of observations. And particularly doing this IgM at high redshifts correctly is actually turns out to be a highly non-trivial task. We now know that ionization, this fundamental question that people ask whether it proceeds inside out, outside in. You now understand everything about it, right? It starts inside out, yes, and later proceeds inside in. So it kind of includes both. And now we know exactly the different analytical models that some of them are based on inside out, some of them based on outside in approaches. We now know exactly where they work and where they don't. And so we can, this whole history of reionization, we can mark the regions in which different analytical models actually work. So we learned, for example, that reionization does not affect global star formation. This is the bad news for JWST people because it's one of the science goals for JWST. It turns out that galaxies which are affected by reionization, this photoapparition effect, don't have molecular gas. And so if we assume, if we make this belief or sign up for the paradigm that stars forming the molecular gas, then reionization would not have an effect on the star formation, global star formation rate. But again, that's something that will be tested eventually by JWST. We also said that maybe that doesn't actually follow metals in the high redshift galaxies, and so by observing them, we'll learn something about how dust actually appears and whether it grows or not, as it comes from supernovae, GB stars, etc., etc. And so the cool things which we can actually learn in the future, right? Just an example of what I could thought. So as I said, we'll probably learn from JWST whether stars form in atomic gas or not. Right? So whether stars only form, or largely form from molecular gas, or whether you can have some sort of non-standard star formation mode in which you can have atomic gas going into stars directly without becoming molecular first. These large-scale telescopes and stellar proximity zones will probably learn a great deal about lives of quasars and finally measure actually their lifetimes, because those will be directly visible in the distribution of proximity zones and ionized bubbles around quasars. As they create those bubbles and they switch off, the bubbles disappear. There will be very interesting constraints on galactic winds by observing not Lyman alpha forest in the IgM, but observing oxygen-1 forest and maybe carbon-2 forest, observing forest of metal absorption species, because the metals will follow the effect of feedback. Feedback puts the metals in the IgM, and that's where we're going to see them. So there will be very interesting constraints, very orthogonal to what the constraints we have from low redshift galaxy formation, low redshift observations on galaxy formation, on this distribution of winds. We may actually end up measuring the escape fraction. That's something that everyone uses, but no one knows how to measure well. But finally, by using 21 centimeter tomography or Lyman alpha galaxy cross correlations, we may be able to pin down the escape fraction. And even maybe we learn something about dark matter, because in at least some scenarios, the annihilation of dark matter actually does contribute to reionization at very early stages. And so using the CMB S4 and maybe 21 centimeter, yeah, I'm almost done, we might actually learn something about nature of dark matter, or at least constrain properties of dark matter in some way. And I'm actually going to conclude. And I think what we're actually entering now is a golden age of reionization research, because the amount of data is going to increase immensely. And it's maybe even new subfields like 21 centimeter, high redshift 21 centimeter would really become like a new subfield of radio astronomy. And so finally, the theory is going beyond sort of simple analytical models. We go into really sophisticated machinery, not necessarily fully simulation machinery. There are actually semi-numerical and semi-analytical approaches which are also competitive with modern simulations. But we're now reaching the precision of theory that allows us to compare with the data on a highly quantitative level, and the future theory will be on par with observations to measure this. And again, the Moore's law only ensures that things will become better. And so I think for everyone who works in reionization, it's a lot of fun ahead. So it's going to be a really exciting decade, and maybe by the end of 2026, right, we meet another first star, whatever, 7 or 8 or 9, right? And we'll say reionization, put a check mark, right? So the good chance it will be solved. Okay.
Okay, so we have time for
pictures,
some questions or comments. Let me see. Chucky?
Yeah, the beautiful matching of luminosity function, evolution of luminosity function, does that mean that you don't need any other feedback sources, or is there still room for like Excel binary or some other sources to contribute?
Contribute to what?
Contribute to the
matching the luminosity function is a part of galaxy formation, right? So we know how to do the feedback. And so it doesn't mean that X-ray binaries do not contribute, for example, to the ionization of the IgM. That will hopefully learn from 21 centimeter measurements and 21 centimeter tomography. But for doing galaxy formation, I don't think anyone proposes X-ray binaries as a way of feedback. And so we know that the feedback is all done by young stars.
What about the supermassive black hole at very high redshift?
Well, those are quasars, right? The quasars are very rare. So they, again, we will learn from Subru whether quasars contribute substantially to reionization or not. But I don't think supermassive black holes affect star formation in galaxies which we observe. I don't think anyone was going to claim that IgN feedback is important for these high-redshift galaxies.
Okay, did I see another hand go up over here? Yes.
Thank you for excellent talk. You mentioned that you can observe escape fraction as function of luminosity function. So is it possible to measure escape fraction as function of redshift or mass of halo by using 21 centimeter tomography and Lima alpha galaxy correlation?
That's the hope. I don't know whether I cannot bet that it's possible, but the hope is that will be something that will put constraints on the escape fraction, because tomography, right, 21 centimeter tomography, if you can observe galaxies in 21 centimeter in the same region, you basically can do photon counting, right? 21 centimeter tells you how many atoms you ionized, and galaxies will tell you how many UV photons you have, and then the escape fraction is a ratio of those two. So there are, of course, details how to do it well, and there's faint galaxies you don't see, blah, blah, blah. But at least in principle, there are ways to constrain the escape fraction, at least with some assumptions. So the hope is that 21 centimeter tomography will actually allow us to constrain escape fraction directly.
Okay, thank you.
Indirectly, I know.
I think Ralph had a question.
So on your very last point, the constraint on dark matter, what specific models of dark matter do you think can be constrained by combining Planck with 21 centimeter?
Well, so with dark matter annihilation is the only astrophysical process that may contribute substantial ionizing photons at redshifts like 20 and 30. So with the next generation CMB experiments, essentially what you would like to do is to measure tau as a function of redshift. Yes. In practice you cannot do it because there's only one sky. But so what you might be able to do is to measure, say, tau between redshift 0 and 10, and tau between redshift, say, 10 and 30. So basically 2 bins. And the second bin will tell you if there's anything non-trivial measured there, then it will tell you that there is some very early sources of ionizing radiation, which probably going to be dark matter.
So
but again, it's a maybe. So depends on the measurement. So
and it only could constrain self-annihilating WIMP type.
Yeah, it's a standard WIMP.
Yeah.
Well, it may actually constrain other models, right? So that which will produce ionizing radiation as well.
Yeah.
But it will put some constraint on the WIMP models that may not be very useful, because it depends on many details, like what's the lowest halo mass, and etc., cross-section. So not every WIMP model produces a measurable amount of ionizing radiation at redshift 30, but some do.
Okay, I think we have one last question here. Yes.
Could you tell us what the major theoretical uncertainty in calculating the escape fraction is at the current time?
I think the whole thing is a major theoretical uncertainty. I don't think you can compute it theoretically. have a very pessimistic view on this, so I try to do it myself. I know how hard it is. So I actually would not believe any theoretical calculation of the escape fraction. I think it can only be measured observationally. And the reason for that is because there's a very large range of where photons are actually absorbed. If you think about a photon that leaves the surface of the young star, some of them will be absorbed in the molecular cloud, actually in the core in which star forms. Then some of them will be absorbed in the molecular clouds surrounding the cluster. Then some of them will be absorbed in the neutral ISM. Some of them will be absorbed in the halo, etc. And so basically, we will never be able to model the whole range of scales that matter. And so we may be able, from theory, to put constraints. If you say resolve everything above 100 parsec scale, you can measure how much you actually absorb on above 100 parsec scale. But whatever happens below your resolution limit, will always be uncertainty. So I don't think you can do it theoretically in a full way. I think you can only do it observationally.
Okay, let's thank Nick again.